Hey guys, Norman here, and hopefully you saw my other video on ceramic glazes. If you haven't, check out the link below. It gives off like a nice sugar-coated way and kind of like an introduction to what pottery glazes is all about. However, in this video, I'm actually going to get pretty scientific. I'm going to get pretty analytical. I'm going to get very well involved with the semantics of how pottery glazes work. I'm going to basically illustrate a lot of the dynamics. It is probably going to get a little bit boring, but there's really no way around it. This is just something that I have to go through. But hopefully, if you are a potter, or maybe you just have some form of mild interest in how glazes work, this video will definitely answer a lot of questions and potential questions. So without further ado, let's get after it. Glazes have four big things that you need to look at, and they are 1. Silica, 2. Flux, 3. Alumina, and 4. Clay. Glazes are basically a glass-like coating, therefore it needs to contain, you guessed it, a glass-like substance, and the most common one used is silica. Silica naturally melts at very high temperatures at around 3,110 degrees Fahrenheit, which can present some problems, but more on that later. In pottery, there are 3 different firing ranges. There's low firing pottery, mid-range firing, and then there's high-range firing. The common way of keeping track of the different temperature ranges is by using pyrometric cones. Cones can range from cone 022 to cone 10. Cone 022 is at a very low temperature, roughly a little over 1,000 degrees Fahrenheit, while cone 10 is at a very high temperature at around 2,350 degrees Fahrenheit. With low-firing pottery, they are usually fired at cone 04, which is at about 1,950 degrees Fahrenheit. Earthenware clay is fired to these low temperatures, and depending on the clay, if you fire them any higher, the clay can melt into a puddle because it's not intended for higher temperatures. Mid-range firing is usually fired to cone 6. Cone 6 is at about 2,230 degrees Fahrenheit. High firing is fired to cone 10, which is at a temperature of approximately 2,350 degrees Fahrenheit. And just understand this, that the temperatures are relative. And actually, here's an illustration of it to prove my point. You can see how complex it can be. But I'm not going to get too much into that. Alright, with that said, let's go back to the silica. It melts at over 3,000 degrees Fahrenheit, which is incredibly high, and that can be a big problem if you want the silica to melt in order to become a glass coating. Now, you can try to fire your pots all the way up to 3,000 degrees or a little over that, but that presents a lot of problems. For one thing, your clay will more than likely melt into a puddle or it'll get deformed. Also, most kilns are not designed to fire to temperatures like that. And another thing to consider would be the utility costs. Therefore, the one and best way of melting silica is to lower its melting point, and in order to do that, you will need to add flux. There are different fluxes out there, such as calcium, magnesium, boron, potassium, lead, sodium, zinc, lithium, and many, many others. There's another material involved in the equation, and that is alumina. This helps to stabilize the glaze and prevent it from melting off the ware during the firing process. And then there's clay. All glazes need clay to help keep the glaze suspended properly. Now this can sound a little bit complicated, but let me take things down to its simplest components. A glaze has glass and clay in it, and then the needed fluxes in order to melt it down. That's it. It is glass, clay, and flux. And when creating your glaze, there are 2 different ways to approach this. There is the theoretical and the practical. And it's necessary to use both. With the theoretical, that's where you read books, calculate a variety of different variables, and try to gain a better understanding in order to establish a predictable outcome. With the practical, that's where you actually mix the minerals and create the glaze, fire it in the kiln, and test it out. Whenever starting things out, it's best to focus on the theoretical so you don't waste a lot of your time with the experimentation process. And the best way to do this is to use a Glaze software program that does the mathematical calculations for you. There are different software programs out there. However, I use Insight Live, which is affiliated with the Digital Fire blog. I like Digital Fire because it contains a lot of information on the science of ceramics. It provides a lot of in-depth information on the different materials used in ceramics. Insight Live is a ceramic glaze software program. Now, before I go any further, this is not an endorsement video. This is just something that I just personally use. Okay, with that out of the way, I'm just going to give you a brief review on the Glaze software part. So here we go. All right, here we go. Let's just get started with this. This is a picture. So here's a picture from my Insight Live account, and this is just an example, you know. But it's the main source of the main sourcing material for the glaze is Ravenscraig slip, which is actually really nice. It's basically a pre-made glaze. So you enter that in, and then frit. That's basically going to act as our flux. But as you can see, this basic batch, the calculations come up to this. Shows me the amount of calcium, magnesium oxide. These right here are fluxes. Calcium, magnesium oxide. That's potassium. That's sodium. Boron is another major flux involved, and that's always something big to pay attention to. And then here's alumina, and it shows the amount of alumina in it, and then silica. And then right over here, this right here shows me the gassing out rate. And you really don't want too much gassing out, you know. If it's up to like 13, 14 or whatever, that could be too much, you know. Calculated expansion, that's another thing to look at as well. And I'll get into thermal expansion and contraction a little bit later. And then as you can see right over here, it's a slightly altered variation of the glaze. I sized down the amount of frit and Ravenscraig and added wollastonite. And wollastonite is a great sourcing material for calcium oxide. And as you can see right here, there's more calcium versus this. And also this has an effect on boron levels, the levels of alumina to silica, because there's been more fluxing agent that has been introduced into the glaze, so that has an effect on the amount of silica and alumina. So if you want a more durable glaze, this makes it a little bit less durable. And then right over here, here's another variation, talc. Talc is a great contributor to magnesium oxide, and as you can see, with the addition of talc, see how much more magnesium is here versus right here. Also calcium levels have been reduced, you know. And another thing too to pay attention to with the introduction of talc, more magnesium oxide, calculated expansion decreased versus over here. But another thing too though, talc tends to gas out more, which means the LOI levels increased compared to wollastonite. Wollastonite doesn't gas out that much, so that's another thing to look into as well. Now, when it comes to the materials, the best place to look them up is right here, just on the Digital Fire blog. As you can see, I'm right here on the internet. Here's talc. It gives out the chemistry format of it, talks a little bit more about it. Here's one about red iron oxide. This is a very common colorant oxide. And then calcining, which I'm actually going to get into that pretty soon. Hold on, let me get to this other glaze. Alberta slip is another great sourcing material for sourcing your glaze. Like, for instance, right here, 80% Alberta slip, 20% for 3134. Here's the calculated mathematical configurations for what it would look like. If I add EPK, the levels of alumina and silica have increased, as you can see right here. And then the introduction of talc, as you can see, magnesium oxide is increased compared to here and here. Now, with Alberta slip in both Ravenscraig, both of them have a lot of clay in it. And Alberta slip, especially, it definitely has clay, and when you apply the glaze onto your pottery, it can crack while it's drying, which can then lead to a glaze defect called crawling. And you don't want that. So what you want to do is calcine some of it. And actually, with calcining, here's an article actually about that, but let's go back to this. But with calcining, basically what you do is you just take the raw powder, and you can calcine Alberta slip, you can calcine EPK, you can calcine ball clay, you can even calcine, basically any sort of clay. Put them in the kiln and fire it to like cone 020 at a very low firing range, just to basically take out the contaminants, or to mostly just to get rid of to get rid of the water content in there, to get rid of the excess water content. And because of that, when you add a calcined material to compensate for having too much clay, when it dries, it'll dry faster, and there more than likely will not have as much cracking, which can then impair crawling. So anyway, that's part of the reason why you would want to calcine your stuff. Now, another thing to look into would be glaze limits charts. Here is actually right here. This is an example, as you can see here. Now, if we're going to fire to, like, let's say, like cone 6, it basically gives you the limits of how much calcium oxide, boron, how much alumina, silica you should have, and every glaze limits chart is conducted by different glaze technicians, and they come up with different sort of conclusions. But just look at those glaze limit charts and then compare them to your analysis, just to make sure that it goes well. So that's another thing that you want to look into too. Okay, well, that basically concludes like the theoretical side to it. Now let's get into more of the practical. So here we go. Okay, now let's focus on the practical side of things. This is pretty straightforward. You want to take the raw materials, measure them out, screen them, add water, and then mix thoroughly. If making a small batch, you can screen the dry materials first and then add water. When making a bigger batch, add water first and then sieve them. With adding water, you will want to pay careful attention you don't add too much or too little. When making glazes intended for brushing, you will want to add less water than if you were to create a glaze for dipping or pouring. When creating a glaze for dipping and pouring, I always measure the glaze's specific gravity. This measures out the amount of water content in the glaze. And if you want to know more about glaze specific gravity, you can actually Google it. There's a lot of information on how to calculate a glaze's specific gravity. After you get your glaze specific gravity taken care of, the next thing you want to look into is the glaze's thixotropy. Thixotropy basically means how thick the glaze is. So for instance, if I am to stir this, and then I stop, 1, 2, 3, it stopped moving. Let me do it again. That's pretty thick. After about 2 to 3 seconds, it stops moving after I'm done stirring it. While something like this is less thixotropic. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, stop moving. That's 12 seconds. That is less thixotropic. Thixotropy is very well affected on water content. That's one thing, but another thing to look into would be whether if the glaze is more acidic or more alkaline. Now this coincides with floculant and defloculant. Floculant, defloculant. Those terms you need to know. A floculant glaze is more acidic, so it's more thixotropic. And a glaze that's more defloculant is less thixotropic and more alkaline. And if you want to alter it, like let's say with this glaze, this is more alkaline. Let's say I want it to be more acidic. I can add Epsom salt or vinegar, and that will make it more acidic, making it more floculant, or giving it higher amounts of thixotropy. This right here, This glaze is very thixotropic. It's very acidic. If I wanted it to be more alkaline, I would have to add something called a Darvan 811. So you can add Darvan 811 as a way to defloculate it to make it less thixotropic. Hey guys, if you want to know more about glaze thixotropy, glaze measuring a glaze's specific gravity, you can actually go on YouTube and look at videos on that, or go on Google and you can be able to figure it out. Yeah, you can even go onto the for me, what I do is I like to go on the Digital Fire blog, and it has a lot of good, a lot of good information. And even Tony Hansen has a YouTube channel, and he basically runs, through the whole process of what he does in order to measure a glaze's specific gravity, how to calculate it, along with glaze thixotropy. So you can even check that out if you have any questions about that. I'm not really going to get into that too much. Now what I want to talk about is our glaze defects. There's like 5 different glaze defects I want to talk about there. That's crazing, shivering, pinholing, blistering, and along with crawling. With let's first talk about crazing and shivering. This is a glaze defect that really the core of its problem really comes from thermal expansion and contraction. Crazing, that's where you see cracks in your glaze. Shivering, that's when bits of your glaze are falling off. For instance, let's say I glaze a mug. I put it in the kiln, I fire it, I take it out, it looks pretty, looks wonderful, all that, and then I decide to use it. And after about 3 weeks down the road of me using it, I start to see parts of my glaze falling out. Well, that's shivering. Now let's say this. I have my mug, I take it out of the kiln. After 3 or 4 weeks down the road, I start to see some cracks formulating. Well, that is crazing. What causes it comes down to a thermal expansion contraction type of thing. Now, if you don't know, everything in the world expands and contracts in some way or form. For instance, this is evident with water, with wood, metal, and same thing with clay and glazes. So, when a glaze expands and contracts quite a bit, and during that contracting process, there's this tight fit on the clay body, and it puts all this pressure on the glaze and it cracks. That's what causes crazing. Now let's talk about shivering. The glaze doesn't expand as much, doesn't contract as much. The clay body tends to expand more and then contract more. And when the clay body contracts more than the glaze has a bit of a loose fit on the clay body, and then bits of your glaze fall out. That's shivering. To solve this, you want to either increase thermal expansion in your glaze or decrease thermal expansion in your glaze. It's actually much more common for your glaze to craze than it is for your glaze to shiver. That's because clay tends to have lower thermal expansion contraction than glazes. A lot of glazes source their materials from like feldspars and nepheline cyanide, and those materials have lots of potassium and sodium, which contribute to high amounts of thermal expansion and contraction. So it's actually better to source your materials from other different things. You can even use something like Ravenscraig slip. If you're new to glaze making, I recommend using Ravenscraig. It's really nice. And then you can add a frit. And the cool thing is, like, you can have 80% Ravenscraig slip. And actually, in this video, earlier before, I showed a glaze recipe with 80% Ravenscraig slip, 20% frit 3195 or frit 3134, I forget. But frit 3134 is a higher expansion frit. And if your glaze is crazing with that, then you can substitute that with a lower expansion frit called frit 3195, and that might solve the issue. Or you can even use frit 3249, which is even a lower expansion frit. Of course, with that said, you also want to make sure that your glaze is not going to shiver, because you don't want your glaze to have too low of a thermal expansion rate. But yeah, you can start off with that. and that can help quite a bit with that problem. Now, the other problem would be pinholing and blistering, and this really is due in part with gassing out. And then after, like certain materials gas out, the glaze is not able to recover, and then it cools down. It doesn't have the chance to recover to cover up the hole, So then when you got the finished piece, you have pinholing, which is basically little holes in your glaze. That's due to gassing out, or blistering, which is just a more severe case of it. Basically the same thing, but it's worse. And if you're seeing problems with that, you can actually replace materials that gas out more. Like let's say, for instance, you're using whiting. Whiting gases out a lot more than wollastonite. You can replace whiting with wollastonite, and that will help. Or maybe if you're using earthly borate, you may be using earthly borate. That gases out a lot more than something like Fritz, in which case you can use Fritz instead. Now, another thing though to consider is that when you do substitute a material, it will change your glaze, because it's a bit complicated. That's why you should use a glaze software program, and then even after that, you have to act like a detective and sort of, conduct your own investigation and try to figure out the semantics to making your glaze better. But you really shouldn't look at your glazes as a recipe, but rather as basically coming back down to the components of glass forming compound with flux and clay, along with alumina. That's really it. And also, you could look at crystallization, other stuff too. I'm not going to get into all that crap though. That's for another video if I even decide to get into it. But yeah, pinholing and blistering. Reduce the amount of gassing out. Another thing too, you can even alter the kiln firing schedule. For instance, it gets the peak temperature and then let it drop down to about like 100 degrees. Put it through like a 30-minute soak or like a 30-minute hold, and that can allow for the glaze to then like recover and then like cover up the areas where it was gassed out, And another thing too to look into would be like maybe your glaze doesn't have very decent melt fluidity. There might be certain materials that you're adding to it that stiffens the melt too much, in which case maybe reduce the amount of those materials. That's something else you can look into as well. So there's some things about that to help solve the problems when it comes to pinholing and even blistering, which is even more severe. Now let's talk about the issue with crawling. This is caused, let me tell you this. This is what causes crawling. If you glaze your mug, let's say, and you apply the glaze, you allow it to dry, it's taking a long time for it to dry, there's a lot of water content, and eventually the water content goes away, the glaze shrinks quite a bit during the drying process and cracks. And then let's say you take your finger, you try to smooth it out, you put it in the kiln, and then bits of your glaze fall out during the kiln firing. And at the end, you start seeing bald spots, where areas where it's supposed to be glazed. That is crawling. And in order to solve that problem, you want to either reduce the amount of clay content in your glaze, because usually, let's say for instance your glaze has high amounts of clay content. You can either try to reduce the amount of clay in it and substitute it with another material, or you can even calcine a portion of your clay. And with calcining, this you can like just take the actual clay, put it in a kiln, fire it to a low temperature, cone 022, cone 020. You can even, you can just try cone 020. That's what I do. And you don't want something really high fire. You don't want to introduce your raw materials through a really high fire, because it can cause damage to it. It can alter it a bit. It can maybe burn it out, And there's even been times I've even taken raw materials and fired the cone 6, calcined it at that high temperature, and the raw materials actually solidified into a rock, basically. So I don't calcine, anything really high. I just go with cone 020. It works well with me. And you can calcine either clay, you can calcine oxides to make stains, whatever, But the thing with clay, though, when you calcine it, it purifies it a bit. It takes out the excess water content, which then makes it melt better during the glaze firing. But another thing, too, when you apply the glaze, because it has less water content, it doesn't shrink as much. So therefore, it can solve the problem with crawling. Another thing too would be maybe you have too little water in your glaze, in which case you can add a little bit more water content. Another thing too that might be causing crawling would be your glaze is way too acidic, in which case you can add Darvan 811. That'll make it more alkaline, making it more defloculant. That can help as well if you were experiencing crawling. Well, hopefully anyway that helps with that. If you want to know more about glaze defects, there's a lot of things on the internet or even on books about the matter. But now I'm going to be moving on to kiln firing, to the kilns. The kind of kiln firing process has a very big effect on the quality or the look of your glaze. For instance, if you're going through an oxidation process or a reduction process, that's actually two different variations of kiln firing. There's oxidation and reduction. Let me first start off with reduction kiln firing. With reduction kiln firing, the source of the heat comes from flames, from fire. And when there's fire, it takes in the oxygen in the environment and then releases carbon dioxide. And so with reduction firing, there's more CO2 in the kiln's atmosphere, which can play a big role on how the different chemicals and minerals interact with the CO2 around. For instance, like iron really reacts very much when you have excess amounts of CO2. That's why with a lot of reduction glazes, you'll see these iron spots, because iron's very responsive with the excess amounts of CO2. And reduction kiln firing has been around for centuries. And then something that's been relatively new is actually electric kilns. Now electric kilns, and this is actually an electric kiln right here. Let's get it closer in. This is an electric kiln right here. Okay, those wires right there, those things right there, those are elements. And the elements during the kiln firing process, they warm up and that's really where the source of the heat is coming from. But this is these type of kilns, they're electric kilns, and they don't get their source of heat from flames. So as a consequence, there's more oxygen in the kiln's environment. That's why it's called oxidation firing, kiln firing, oxidation. And when you have, here, let me lower the lid again. So during a oxidation kiln firing, the chemicals and the different minerals interact differently compared to like with reduction, where there's more CO2. With more oxygen, like for instance iron, doesn't respond as much. It tends to kind of stay back more, so you don't see as much of the iron spots. With oxidation, you tend to get more like brighter, more vivid colors. While with like reduction, you tend to get darker, more earth tone type of colors. For me, I don't do reduction kiln firing. All the pots that I make along with my dad are with these three different electric kilns, all done through a oxidation kiln firing process. Now, with that said, I want to talk about kiln firing schedule. Like with this kiln right here, this is it's a computerized kiln. I like it because you can install different kiln firing schedules to it. You can schedule a specific rate that you know of how fast you want the temperature to climb. You can then schedule holds. You can also have a slow cooling process, which when it comes to glazes, they crystallize during the cooling process. And you can even get iron to respond more so with a slow cooling process, at least from what I've seen from my own observations. So you can get some different effects with that as well too. So kilns are something very big. I'm not going to get anything more into that. At least that kind of summarizes things. Glazes are very well affected by the kind of kiln that you're using. Anyway, thanks for watching this video. This was a bit of a lengthy video and pretty technical, but I made this video because I just wanted you to understand a little bit more of the things that I go through in order to create the different effects that I create. Thanks for watching, and hopefully this video was helpful and educational. Anyway, thanks and take care.